Okay, so earlier this year, I organized a series of talks by scientists on the positive aspects of climate change in order to inspire artists to submit an art piece to a fall show at the Corvallis Art Center entitled, "What Will Nature Do?" The show will take place in October in Corvallis. Meanwhile, this spring term series of talks, co-sponsored by the OSU ART-SCI group, the Corvallis Art Center, and the Department of Biological and Ecological Engineering, is by scientists who are also artists, or artists who are also scientists, with the goal to explore how their science might inform their art, or their art might inform their science. Today, it's my pleasure to introduce Chet Udell, who was born in rural Ohio when David Bowie released the album Let's Dance. Growing in the ancient cypress swamps in Wewahichka, Florida, Chet completed his PhD in music composition with cognate in electrical engineering in 2012 from the University of Florida. He's an inventor on domestic and international patents on wireless sensors, a father of a 5-year-old, and thus an assistant professor in biological and ecological engineering at OSU, the director of the NSF and USDA-funded openly published Environmental Sensing Lab, and the director of the CLA Arts Research Technology and Expression Initiative. So without further ado, Chet, it's my real pleasure to invite you to this series, and thank you so much for being here.
Thank you very much, Dominique. I appreciate it. It's a pleasure to be here and meet you all. So I'd like, Dominique, would you be able to enable screen sharing for me?
Oh, yes, of course.
Excellent. Put together a little slideshow for everyone.
Yes. Let's see.
It's just a bunch of pictures with green days. I hope you had the time of your life. No, I'm kidding. Let's see here. All right, I'm gonna go to full screen. So hey everybody, my talk is on instrumentation, environments, and musicianship. And so let's see, I wonder if I can go into full screen. Here, do you all see, is that full screen now?
Yes.
Perfect, great, thanks. So my work sits at the intersection of music and engineering, and I do a lot of stuff with those two things. And it's funny how music has enabled me to do engineering, like ecological sensors, in an interesting way. And it's also enabled me to do music in an interesting way. So these two really feed back on each other. So keep going. Go. There we go. All right. So I went to a small liberal arts college called Stetson, and then got my PhD and master's in composition with electrical engineering. In a previous life, I taught music technology at the University of Oregon. I've been a CEO of a technology startup company, have some patents going on. And these days I'm an assistant professor in biological and ecological engineering. I direct the openly published Environmental Sensing Lab, and I'll tell you a little bit more about that in a while. We were established in 2016. And this recent year, I've been brought on by the Dean of the College of Liberal Arts to direct the Arts Research Technology and Expression Initiative. And we're a collective of faculty from across the liberal arts, engineering, forestry, like all kinds of the places. And I'm really looking forward to meeting you. And if you're interested in joining us, one of our main missions is to create cross-cutting curriculum. So we take a look at all the classes that we teach, the kinds of concepts that we want to do, and try and coordinate these cross-cutting ideas across different technologies and creative practices. I'd like to play a little portion of a video to get our minds primed for what I'm about to say.
3,000 years.
There we go.
Roughly 43,000 years ago, a young cave bear died in the rolling hills on the northwest border of modern-day Slovenia. 1,000 years later, a mammoth died in southern Germany. A few centuries after that, a griffon vulture also died in the same vicinity. And we know almost nothing about how these animals met their deaths. But these different creatures dispersed across both time and space did share one remarkable fate. After their deaths, a bone from each of their skeletons was crafted by human hands into a flute. Think about that for a second. Imagine you're a caveman 40,000 years ago. You've mastered fire, you've built simple tools for hunting, you've learned how to craft garments from animal skins to keep yourself warm in the winter. What would you choose to invent next? It seems preposterous that you would invent the flute, a tool that created useless vibrations in air molecules. But that is exactly what our ancestors did. Now this turns out to be surprisingly common in the history of innovation. Sometimes people invent things because they want to stay alive or feed their children or conquer the village next door. But just as often, new ideas come into the world simply because they're fun. And here's the really strange thing. Many of those playful but seemingly frivolous inventions ended up sparking momentous transformations in science, in politics, and society. Take what may be the most important invention of modern times, programmable computers. Now, the standard story is that computers descend from military technology, since many of the early computers were designed specifically to crack wartime codes or calculate rocket trajectories. But in fact, the origins of the modern computer are much more playful, even musical, than you might imagine. The idea behind the flute, or just pushing air through tubes to make a sound, was eventually modified to create the first organ more than 2,000 years ago. Someone came up with the brilliant idea of triggering sounds by pressing small levers with our fingers, inventing the first musical keyboard. Now, keyboards evolved from organs to clavichords to harpsichords to the piano until the middle of the 19th century, when a bunch of inventors finally hit on the idea of using a keyboard to trigger not sounds, but letters. In fact, the very first typewriter was originally called the writing harpsichord. 1,000 years ago,
Right.
at the height.
So let's see, escape out of there. Uh-oh, it's gonna have me redo that. So what happens? There we go. All right. Yeah, and so I'm really interested in this idea of the coevolution between our current technology and how it evolves alongside of musical instruments. And here we go. Okay. And yeah, I think musical instruments are really interesting because they're kind of, confuse art versus artifact. And they're frozen structures of things that represent the technology, the cultures, materials, methods, the practices of any given time. And musical instruments are really cool in that they enable humans to express themselves by converting physical gesture into sound. So they extend human anatomy. And these things take into account all sorts of stuff that are inherently human, like our size. Do they fit in our hand? Are they a certain kind of agronomic shape? They must be playable within our certain attention span. We're talking immediate response or milliseconds, seconds and maximum. They convert a certain kind of human energies and motion into sound, and they're typically fairly fragile. Like you can't leave a violin or a piano outside in the elements. So they must be, they're designed to inhabit the environments of human beings. And that's kind of the reason why we don't see drum sets that are 10 feet high, or a harpsichord that's the width of a hallway. We tend to get instruments that are unique expressions of things that translate our natural movements into sound. Typically, acoustic instruments are comprised of two things. Driver, which is the thing that is expressing the physical energy in the system, or what we call actuation. And then the resonator, which is some kind of cavity or material body that translates that physical energy into the acoustic resonance. And usually the relationship between the sound we experience and what we see are very causal. However, something happened in the 1700s, and Benjamin Franklin discovers electricity. This is a true historical account. Uh, and it completely broke this idea of our physical energies translating into the sound itself. So we need transducers in the realm of electronic instruments, and instruments are transducers. Loudspeakers are another kind of transducer that convert one form of energy into another. So for a loudspeaker converts electrical wiggles and current into wiggles and vibration of a diaphragm that creates wiggles and air pressure for our eardrums. So in the realm of electronic instruments, we have your physical gesture and we have the sound, but in between, we have this interface layer, which is sensors. And sensors are very much like the eyes, ears, nose, mouth, touch on a human body, except they enable things in the environment to be translated into electrical impulses that computers, and we can translate into data. Those kinds of things we can work with. All right, well, let's think for a moment about environmental instruments. Like, how are environmental instruments similar, and how are they different from musical instruments? And in 2016, I made the conversion from being a musical instructor over to being professor in bioeco engineering, doing environmental sensing. And so this was a question I had to really think about in my mind, like, how transferable are these skills really? And so environmental instruments enable us to discern patterns about our world by translating energy and motion that we cannot easily observe into forms that we can. And so if you think about a thermometer, this mercury type of thermometer here, is a very simple way of converting something that really, we can only perceive through our human sensations in a very general kind of way, very subjective kind of way. And by using these mercury thermometers, you and I can look and see that, oh, this is exactly 90 degrees. It is not just hot or cold, but we can say what it is. And environmental sensors go beyond our human anatomy. So these things typically take on many different sizes. They convert all sorts of energy and motion types, like evaporation, CO2, solar radiation, soil moisture, seismic vibration, on and on. So things that humans just don't express at all. The time and the attention spans are very elongated. We're talking sampling periods of minutes, hours, days, even occasionally years. So if you're talking about drilling an ice core, then we're really on the resolution of years, if not hundreds of years. All right. These are typically made for uninhabitable conditions. Like, they're rugged. They're made to live in places on the ocean floor and in very hot, lava type places. They're not places people typically hang out very long. They're not usually spectator devices, so people don't like sit around watching them. They don't do anything interesting on a human time scale, really. And the data is almost always useful in over large amounts and in non-real time. In other words, these sensors collect data, drop them onto a spreadsheet of some kind, and then the scientists go back and do all kinds of really fun stats and analyses to create the meaning from that. And also, I don't know about you, but looking at these, they're not quite as visually appealing as looking at something like a harpsichord or a violin. Maybe some engineers get a great deal of pleasure out of looking at this and maybe find these more aesthetically pleasing than a violin. But I can't get over how much better a violin looks. All right. So, but if you take a look at how similar these things are, we have environmental and energy motion. And on the other side, instead of sound, we're talking about observations or responses. And in the middle, we have this very similar computing layer. We have sensors that translate things in the environment to electrical impulses, and then that gets put into the realm of computing and data for us to work with. I think where all these things maybe come back together in the end is that once we've gotten to our sound layer or observational layer, that then we use semiotics to translate these things back into meaning. So like, what does music actually mean? Or what do these scientific observations do for us in the end? Like, what kinds of insights and conclusions do we draw from that? So I joined the openly published Environmental Sensing Lab. I helped found it with our PI, John Selker, in 2016. Is a National Science Foundation and USDA funded effort. And kind of what is going on is we live in a really interesting time where a digital file can become a physical object through 3D printing. We have a huge and growing community of do-it-yourself the maker community, and these people get off-the-shelf electronics and they tear open the warranty, they void warranty on things, and they just dig in and really create customized solutions to everyday problems. And so these technologies are really well poised to transform environmental sensing. However, the researchers who are asking the environmental, ecological, agricultural questions trained for a very long time to do their science very well. They aren't necessarily trained in electronics or programming or 3D printing. So to expect those researchers to make that quantum leap and start applying these capabilities into their science to advance instrumentation is a very tall order. So this is where we exist, is where a conglomeration of 50 fully funded undergraduate students on various research grants. They're across environmental, electrical, mechanical, and computer science. And they are the leaders. They actually are the professional designers in the driver's seat designing these transformational instruments. And they collaborate with the researchers to essentially advance what we can monitor or measure and the kinds of questions that we can ask. And so with only a few pieces of equipment, you can actually do a lot. So we have laser cutters, 3D printers, electronic stations, and we've been able to create some pretty interesting environmental instruments. One of the instruments we're kind of proud of is this thing called a dendrometer. And what's super cool is plants, they vibrate. Plants expand and contract. And they do this with the diurnal fluctuations. That's the sun going up and down. And as they're pulling moisture out of the soil and doing their transpiration thingy, they tend to vibrate more or less in amplitude based on their stress. And these stressors could be things like lack of water, disease, I don't know, they don't like their neighbor for some reason, they're being strangled by a vine, who knows. But we can tell an awful lot about measuring these plant vibrations. So we created a magnetic plant vibration monitor with a 0.5 micron resolution. They communicate over long-range radio. They take a sample every 15 minutes. And this is our temperature, and this is what the displacement was. And I want you to notice an anomaly here. As the temperature goes up and down throughout the days, we typically see a rise here, but there's something weird in the middle. And we thought that was kind of strange. Maybe our sensor is off. But we actually calculated another thing called the VPD, so the vapor something. Dominique can
pressure
probably
deficit.
Yeah, there we go, the vapor pressure deficit. And so and basically what we saw was that just for that particular day, the vapor pressure deficit really didn't do an awful lot. And so we didn't see a response in the plant. So this is actually a really awesome validation of our instrument here. We work with a person up in Alaska who collaborates with the Chilkoot tribe, the native tribe there, and they're really interested in tracking salmon. The scientists are interested at this from like an ecological and endangered species kind of place, and the natives are interested in this from these are sacred animals in their culture, and so we have mutually beneficial relationship here. And right now it's very hard to collect what we call eDNA samples. That's actually drawing DNA out of the water by pushing stuff through a pump. And people have to go out there in person, can only do one sample at a time by hand. And there are auto samplers out there, but they cost about $30,000. And so we decided to try and disrupt this market by creating an open source eDNA water sampler that lets people put a 24 sample capacity box out in the environment and leave it there for a month or two, and then come back and they have all of their samples preserved in these ethanol containers. And that way they can take them back to the lab. And there's a little software app that we created that enables scientists to program this in the field. And the city of Sitka suffered some catastrophic landslides a few years back, and the National Science Foundation thought it would be good to create an initiative to fund some landslide research. And so in partnership with the University of Oregon, we've created these landslide monitoring sensors that detect soil porosity and pressure, soil moisture, soil temperature and relative humidity. And we also have a tipping bucket that measures, I think it's like every milliliter of water coming in. So high resolution tipping bucket. And the scientists use all of these metrics as a proxy for predicting landslide risk. And so typically you're going to get a lot of activity. There's kind of rhythms in the world. And the rhythm of landslides is very active in the wet season and not so active in the dry season. And so a variety of scientists use these sensors to help predict these at-risk zones here. So that was kind of my brush with environmental sensing, but I also create instruments for creative expression. And in doing all of these environmental sensing projects, I feel that it's really opened up quite a big world for me to be able to create customized musical instruments for creative expression. And likewise, because I have this like really playful, exploratory attitude, and in making these instruments, you fail a lot, that I've been able to instill a lot of these design philosophies onto my environmental students who are creating these other instruments. And so it's been a really fun feedback loop. So a couple of projects I'll share with you is one called the Spider Harp. And I did this in collaboration with Ross Hatton, who is a professor in robotics at Oregon State. Andrew Otto was a PhD student at the time. He's now Dr. Andrew Otto. So that's fascinating. I'll share this video.
A spider harp is a scaled up version of a classical spider's orb web. We were inspired to make the spider harp because we were already looking as a scientific project at understanding how spiders' senses worked, how the vibrations traveling through the web, what kind of patterns spiders would be looking for in order to understand from the biological end how their senses work. At the same time, we realized, hey, if we've already built a large-scale model so we can investigate this, and our implementation of what we think the spiders are doing is so good that we can tell you which string is being plucked on the web, then this sets it up very nicely for an instrument. And the scale was already about the size of a harp, so it lent itself very naturally to being turned into a musical instrument.
I'm Chet Udell, and I'm an assistant professor in biological and ecological engineering, and I also direct the OPENS Lab. It stands for Openly Published Environmental Sensing. I'm a second-year professor here, and so my first year I came in and I saw this special on the BBC about this wild robot spider that can detect position of vibrations on a web. I'm always looking for new ways I can create musical instruments. Yeah, we met up and I was like, you know, your robot spider would make a really great harp. And he's like, yeah, this would make a really great harp. So we decided to collaborate. Vibrations are sound, and so we're using accelerometers to translate those vibrations into fluctuations in data. That data enables us to analyze that sound, and so we're just basically translating sound into a program that lets us analyze it in a computer and then figure out all kinds of stuff about where those vibrations are coming from. All right. So the components of the spider harp is comprised of this orb web we've got going on here. When we have accelerometers on the feet of the spider, some computer software that translates the location data. So the spider is tracking position, amplitude, and how far away it is. And then essentially we're using that like a MIDI keyboard data. And I've laid, we also have 8 speakers, what we call octophonic speakers, that are placed around the audience or around the web that will immerse the audience into this octophonic sonic space. And I've, kind of in a nutshell, like how it works is if P is the position of where you're plucking it, that causes A and B, these, what we call, so these are the radials, these are the, shoot, I blanking because of the performance anxiety. Anyways, these black strings here are going to be very similar in vibration, and they're going to be inversely similar 180 degrees out of phase from the pluck. And so you can quickly choose the which 2 quadrants are going to be the most likely where the pluck is at, and then you can use a time of flight to determine the delay, where basically the vibration is going to reach these 2 pair quicker than these 2 pair. And that's how we can determine really quickly the quadrant it's coming from. And then the string is actually, we tune the web. So we tune this web as if we would tune a guitar. And there are tuning pegs on the ends of these. And if you tune each of these strings to be the exact same tension, then what you end up with is a longer strings up to shorter strings. And we know, because Pythagoras did a really cool essay on it, on vibrating strings, that smaller strings with the same tension, shorter strings going to be higher pitch, and longer strings of the same tension going to be lower pitch. And so the spider is actually listening to the pitch of the strings and translating that into positional data. And so I kind of laid this out like a circular keyboard. And so I had do, re, mi, fa, sol, la, ti, do. And then I laid out the octave classes where the shorter strings would be higher up and the longer strings would be lower. And what this kind of affords is that if you know a melodic pattern, like Itsy Bitsy Spider, you can play that melodic pattern in a low register by playing on the outside, but keep the pattern the same exact and play the same melody, but up higher by playing in the center of the web. And so I thought that that was a pretty, like, if a spider were a keyboardist, like how would a spider sort of like play the piano? And so that's kind of what I came up with. All right, and then other instrument I'd like to share with you is the optron. And the optron is kind of what you would get if a lightsaber and electric guitar had a baby. And I'll show you this little brief performance.
I want you all to meet Chet, and I actually think that J.J. Abrams should meet Chet. So this is something that's very from another galaxy.
Far, far away.
Yes.
So
Wow, that was exciting.
All right, so the Optron, I basically got a shop light from Home Depot, took the LEDs out of it, and put in 144 of my own individually addressable red, green, blue LEDs, and put a microprocessor in there, put some sensors. Oh, these are the LEDs there. And put some sensors in there, like something that'll track my hands, and a linear position and pressure sensor for a fretboard thing, and a motion sensor. And in this version, I use the computer vision. And so I have a camera that is using OpenCV to track the color and position of the lights of the Optron. And that is then being transformed into sound. And so you have light being transformed into sound. And so I called the first track photosynthesis. And that was a performance at the Guthman Musical Instrument Competition at Georgia Tech. Wired Magazine calls it the X Prize for New Musical Instruments. I've been a 4-time international contender at that conference, and this particular one won the People's Choice Award for Best Performance. I was proud of that. And so the future of the Optron is we have the Optron Pro right here, which has electronic strings that you can play with your hands. And I put some wireless hand trackers, so you can actually put your hands in front of the light bar and interact with the lights. And then a better fingerboard for aftertouch. And I'm working on these cute little 12-inch versions of this for STEM education and a suite of software. And so it's like this cute little thing that, like, it's pretty inexpensive, and putting together a suite of software and exercises to help inspire STEM arts educational activities. And Victor is actually one of the people I'm working with to do these activities here. Oh yeah, they are. I really hope that's working out for you. We gotta chat about that sometime. Make sure you got what you need. So, yeah, I want to kind of end this not with conclusions, but more with questions, because like I'm always kind of asking myself, where can I go? Like, what can I do to kind of continually bridge these two passions in my life? Are these two approaches mutually exclusive? That is, can you only do one or the other? And I mean, this is kind of my mindset. Is the thing that's paying my bills is not the creative stuff. I wish that was the case, but the engineering things are what's really getting the grants and keeping the lights on. And I do think that maybe there is something systemic in our culture that values the intellectual, the left brain analytical kind of sides of things, that component of science. But oftentimes I feel like the creative expression of these sciences and using these to open up to audiences could actually be really a really cool way of not only communicating your science, but also thinking about how to make scientific instrumentation and observations and analyses in kind of a more out of the box and kind of creative way. For those interested in fast Fourier transforms, we all know that the time domain is inversely correlational to the frequency domain. And what I mean by that is there's this phenomenon in these kinds of analyses where you can either measure something highly precise with a high temporal resolution, so a high sample rate, and know very close when an event is happening. Or the trade-off is you can know with high precision the value of a thing. So in the case for sound, we're talking about the frequency. So how dead on precise are we going to be with the frequency analysis? But we have to throw out how accurate it is with the time, the precision with the time. And I think that this translates well to this phenomenon that I'm experiencing in environmental sensors or instruments for environmental sensing versus instruments for creative expression. namely that, again, talking about the time scale, environmental sensors need to be highly precise with the thing that they are measuring, whether that be temperature, seismic activity, sound, solar radiation. Like generally, the more precise you can get it and accurate you can get these things, the better you are, like the more confidence you have in your observations. We're not so concerned within like a minute or 15 minutes, like exactly when that sample happens, just as long as it's like in that 15-minute bucket for many things. However, for the instrumental kinds of expression, you need to be instantaneous or highly precise with like that temporal response. Like when I do a thing, I need to hear a thing that corresponds to it. And any lack of that really can get offbeat and jarring to the experience. But you can take some creative liberties with the data. So the data can really co-vary with your sensor instruments as long as it kind of wiggles when you wiggle it and it wiggles that sound in a co-varying way, great. Like you don't need to know to like the 10th decimal place, like what that thing, like how precise that thing might be. So I don't know, that's just kind of one of how they're very different. But we do know that there is a growing disconnect with social awareness and how environmental science translates into policy, and how policy is so much driven about public awareness of an issue. And really, like there is a crisis going on, and like if people like actually felt like just how in how much hot water we are right now, I think there would be a better, I think there'd be more policy changes that mirror these effects, but I just don't see that. However, art, I think, is a way to really help inspire more awareness about the kinds of things that are happening in the sciences. And we do have an opportunity where a phenomenon happening can easily be translated into arbitrary data. And once you have this arbitrary data, you can transform this into virtually anything. So what if solar radiation could become a musical tone, or seismic activity could trigger a melody? And there are quite a few projects out there that do things along these lines. And I kind of have been thinking about, how am I going to bridge these two practices I have right now? And, can play and creative expression be seen as integral to our process, like how we make scientific instruments and how we communicate science? Thank you.
Thank you, Chet. Well, that was an interesting talk. You lost me a couple of times, but that's normal. I'm not a musician, so it's like, but it sounds really cool. I was very curious. I'm going to ask the first question. I'm asking all the participants, thank you for being here, to write their question in the chat so that Chet can read the questions and answer them. But my first question was about your dendrometer. One thing that's been happening with climate change is, there's when the vapor pressure deficit is so high, the trees cannot pick up the water fast enough. And so there's embolism that's happening in the tree, and you can actually hear the pop of the vessels when there's a bubble of air that comes through. It would be really cool to have trees instrumented with that and do something with that popping. And that would be kind of a scream that could be, passed on to people saying, you need to do something, water or something. Miss the trees so they don't die, because usually that's what happens. There's high mortality after embolism. So anyway, but it would be a really cool thing to do.
Yeah, certainly. Yeah, that would be really cool. Yeah, we've sort of had this idea of creating a Twitter account for each plant and having the plant be able to tweet like a Likert scale, 1 to 5, how sad or happy it is, or how stressed out it is. And we thought that would be hilarious, but we haven't gotten to that part just yet.
Yeah, well, that would be less than hilarious. It would be like, hey, help me. A cry for help. That'd be really cool.
I've actually seen somebody on the internet that I'm not sure if it's a dendrometer or if it senses like the electronic impulses, but they hook stuff up to mushrooms and then they make music from that.
Oh, wow.
That's really cool.
I don't know if you've seen that, but it might be worth searching.
Oh, feel free
Neat.
to send me a link.
Yeah.
I see
tr-
a question here by Cynthia. How much is aesthetics important for your instruments, or how do you work on improved design aesthetics of them? That's a really great question. I think that if you kind of take a look at where's that first version of the Optron, I've never been a visually aesthetic inclined person. That's why I went into music. So the first version is just a stage light or a shop light with a couple of sensors like taped on there. However, every subsequent iteration, gets better. Every subsequent iteration gets better and better. And so I think that, I would say aesthetics is important to me, but it's definitely a secondary consideration. I think the first thing I'm interested is like the gesture to sound aesthetic translation. So is it like when I move this thing, does the sound that I hear make sense with that motion? And how do I optimize that first, and then kind of build the art around that after. And for the environmental sensors, it's definitely just not a consideration at all. We like to stay on brand by choosing orange boxes to represent OSU, but that's kind of basically where we stay right there.
I would say that in and of itself is unaesthetic. Sorry.
Right.
Uh,
Thanks for the link, Victor.
yes. Any other questions from our audience?
So I guess one of the things that I hope for with these lectures, where it's artists or people who use their scientific practices in their art making, what advice would you give to artists who because many of the artists who sat in on a lot of the science lectures, I'm just so disappointed there aren't more artists on this artist lectures, but what advice can you give them for implementing some of these ideas and concepts that you all are sharing into their artwork? Because a lot of them are pretty traditional in their scope of what they do, and or are very interested, but tend to make artwork that at the end of the day feels too literal to them. And the magic of the artwork that they typically do is in the magic piece of it. So, and you certainly, we've seen that in the instruments that you're making, there's a lot of magic in them, but so I'm just thinking how to translate this. I mean, all of this is so fascinating, but for an artist who's like looking for that, kernel.
Yeah. Wow. I mean, that's a big question. I'm kind of inclined to say that you can break a composition or a piece of art down in I think 4 components: form, structure, materials, and method. And I think that if you choose to give up agency of one of them and replace that with a ecological or a environmental phenomenon, and let that figure out a way to, like, if your materials, maybe use only natural materials from like a certain site specific thing, or the structure of a thing might be, get a bunch of data from seismic activity waves, and that's like what that's the thing you're gonna work with there for your structure. So I would say kind of be open to what nature might be already delivering, and just kind of see what kinds of unique things might happen. And it probably, I don't know, the initial idea isn't going to work maybe, but I think that the practice of trying it out might reveal the way to do that. And then, yeah, I just, I think a different answer might also be, I'm just really inspired by enchanted objects, and just kind of thinking about the things that we do today. And you think back like 30 years ago, what was possible. Like I always wanted to, like, as a kid, pause the TV show or like rewind it so I could like see a part again. And now it's everyone's doing that. Yeah. And like this is it's kind of what I wanted, not at the time. And so yeah, I think that, when I am very, I think like having that imaginative thing be the drive behind the thing that you make.
Yeah, so a colleague I'm quoting a colleague. I was looking for the paper, and it says the main challenge is the lack of human imagination, our inability to see a different future because we're staring down this dystopian path of pandemic, climate change, and biodiversity loss. So it's like, yeah, imagination is really key. So I have a question for you, Chet. So the art show that the Art Center is going to be having this fall is about, the positive aspect of climate change, or, imagine a future that will not be just doom and gloom. So how would you approach that with musical instruments? And, you could measure some happy trees and some, not so happy trees, but apart from that, it would be kind of a cool thing to prepare, a symphony of sound that would be measured from nature or something like that.
Right. Yeah, I would, my mind gravitates towards, making a piece out of water or water instruments or something, just because, given the rising global water surfaces, there's gonna be a lot of that around.
Yeah.
Maybe not all entirely potable water, but
Right, salt water mostly.
it's gonna be much more salt water around.
Yeah. But it would be
Yeah.
a cool thing to think about. It'd be cool if you could prepare something for this fall.
I would be very curious about that. Yeah, definitely keep me posted, and if I can submit something,
Yeah.
that's a very curious idea. I like focusing on the positive aspects.
Yeah.
One thing might be Corvallis is going to end up being, our climate's going to be a lot more like North California. So not arguing about that. That's kind of nice.
Yeah, definitely. Yep. Okay. Any other questions? We
I
need
think,
itsy bitsy spider recording for the show. Yes.
Yeah. And Victor had asked about the OSU Arts Research Technology and Expression Group. So
Yeah.
we don't have a website just yet, but we do meet up periodically to go over goals. And so if you want to join, I would be much obliged to take your info down and loop you into our group.
So what are the criteria to join a group like that?
Well, basically, you just need to be in a certain discipline and interested in mixing ideas and of other disciplines. And so there's not a lot of. It's actually kind of a broad network, but the things we want to achieve are things like. So 3 of us created a set of classes that all feed back on each other for various arts technology concepts. And so I teach a sensor tech in the arts class. The video professor teaches a projection mapping class, so getting things off the screen. And the other professor teaches like kind of a hardware hacking. So go to Goodwill, take things apart, and make sonic sculptures or interactive art pieces based on stuff you've taken apart. And you can jump on at any time in that 3 class rotation, and concepts you learn in one class have value in the other class. And so just kind of looking for synergies like that. I think another thing is just helping us recruit students. So we also have a student club called the STEMbassadors, and it's an official OSU organization. And it's a really great melting pot of artists and musicians and computer science students, mechanical engineering students. And they're helping build all kinds of really fun projects and make neat things. One is we're doing an art installation for, this is Kalapuya land, and we're creating something called the Beaver Cart, and that stands for Big Electronic Audiovisual Rover. And it's got a portable sound system, a short throw projector, Wi-Fi, like all kinds of stuff. And then basically is like a mobile multimedia guerrilla style command center. And so you can roll up to anything and have essentially a multimedia studio for kind of a guerrilla style art music technology collective.
So instead of having those little robots bringing food to the dorms, they might soon be little robots bringing all sorts of art shows and music to the dorms. That would be cool.
That would be great. Yeah.
Great. Well, it is 1 minute to 5, so I guess we can close now. Thank you very much, Chet, for this talk. It was great. Really, really amazing. Really cool stuff.
Thank you, everyone.
And thank you, everybody, for attending. And next week on Tuesday, we have a talk by Leah Wilson and Steve Wanzel. And so Leah and Steve work on rivers. She's the artist and he's the scientist. So we'll see how the two match their skills. Again, thank you very much. And we'll see you next week.
Thank you.
Bye.
Bye-bye.